All right, let's just jump right in. I want you to imagine an element that's so incredibly versatile, it can be the symbol of forever, unbreakable love, and at the same time, the humble tip of your pencil. An element that gives your drink its fizz, but can also become a silent, deadly gas. It sounds like something out of science fiction, right? Well, today, we're talking about the ultimate shapeshifter of the periodic table, carbon.
I mean, just look at these two. On one hand, you've got a diamond, the hardest natural substance we know of, just brilliant and perfectly clear. And on the other, you've got graphite, a material so soft and flaky it literally leaves the trail behind, which is how we can write with it. They could not be more different in how they look, how they feel, and how they act.
But here's the kicker. What if I told you that, chemically speaking, these two are identical? That the diamond on that ring and the lead in your pencil are both just pure carbon. Nothing else. How is that even possible? It seems to defy common sense, right? Well, the answer lies in this really fascinating chemical concept that shows us how one single element can wear a whole bunch of different masks. And it all comes down to how the atoms decide to arrange themselves. So there's actually a word for this, and it's allotropy. It's just the fancy scientific term for when an element can exist in more than one physical form. And these forms, which we call allotropes, can have wildly different physical properties, like hardness or color or whether they conduct electricity. But here's the thing, because they're made of the exact same atoms, their basic chemical properties stay the same. The secret, the real magic, is all in the atomic arrangement. Think of this as carbon's family tree. It basically splits into two main branches. On one side, you've got the crystalline forms. This is where atoms are arranged in a superordered, repeating pattern, kind of like soldiers standing in perfect formation. That's where we find our diamond and graphite. And then, on the other side, you have the amorphous forms, where the atoms are all jumbled together without any real order, like a messy pile of bricks. This gives us stuff like coal and soot. To really get this, let's zoom in on carbon's two most famous crystalline kits, diamond and graphite. This is where you can see crystal clear how much structure dictates absolutely everything.
And this right here, this illustrates the difference perfectly. So in a diamond, over on the left, each and every carbon atom is tightly bonded to 4 other carbon atoms. This creates this incredibly rigid and strong three-dimensional network. But now look at graphite on the right. Each carbon atom is only bonded to 3 others. This forms these flat, hexagonal sheets that are just stacked on top of each other, held together by really, really weak forces.
So, what does all that mean in the real world? Well, that rigid, interlocked 3D structure in diamond is what makes it the hardest natural substance we know. It also makes it a non-conductor of electricity, because all of its electrons are locked tightly in those bonds. Now, graphite, with its weak bonds between layers, can have those layers slide right past each other. That's what makes it so soft and slippery. And those looser electrons hanging out within the layers, they're free to move around, which makes graphite a great conductor of electricity. Totally opposite properties, all from the same atoms. A really simple way to picture it is like a fortress versus a stack of paper. The diamond is the fortress. Every single brick is interlocked with all the others, making it unbelievably strong and stable. You can't just push it over. But graphite? That's our stack of paper. The individual sheets are pretty strong, sure, but they can just slide right off one another with almost no effort at all. And this fortress structure is exactly why we use diamonds for a lot more than just pretty jewelry. Their incredible hardness makes them perfect for the tips of industrial drills that have to bore deep into the earth. We use them for tools that can cut glass and other super hard materials like it's nothing. It's pure strength. And what about the stack of paper? Well, that slipperiness is precisely why graphite works in pencils. Every time you write, you're just leaving a trail of those sliding paper-like layers behind on the page. It also makes it a fantastic dry lubricant for machine parts that need to move smoothly. And of course, because it conducts electricity, it's a key component in the electrodes inside batteries. But carbon's shape-shifting ability isn't just for its solid forms. Oh no. When carbon decides to team up with oxygen, it tells another dramatic story of contrast. This time, it's a tale of two very, very different gases. On one side, you have carbon dioxide, CO2, a compound we deal with every single day. It's actually essential for life as we know it. But you remove just one of those oxygen atoms and you get carbon monoxide, CO, an invisible, odorless, and highly poisonous gas, a silent killer. So how in the world can one tiny oxygen atom be the difference between life and death? It's incredible when you think about it. Let's start with the helpful one, the good gas. Okay, so carbon dioxide. We use it all the time. It's the gas that gives soda and other soft drinks their fizz. When you freeze it, it becomes solid, dry ice, which is an amazing refrigerant. It's the gas released by baking powder that makes our cakes and bread light and fluffy. And because it's heavier than air and won't fuel a flame, we use it in fire extinguishers to put out fires. Pretty useful stuff. But now, take away one of those oxygen atoms and the entire story changes. Carbon monoxide is formed when carbon-based fuels don't burn completely. Think of a car's exhaust or a faulty furnace in your home. And its danger? Well, its danger lies in how it completely hijacks our own bodies. And the process is just terrifyingly efficient. When you inhale CO, it gets into your bloodstream and finds hemoglobin. That's the protein in your red blood cells that's supposed to be carrying oxygen all around your body. But here is the massive problem. Hemoglobin binds to carbon monoxide over 200 times stronger than it binds to oxygen. It forms this super stable compound that basically blocks the hemoglobin from ever picking up oxygen again. As you can see here, your body is slowly and silently being starved of the oxygen it desperately needs to survive. And the result, as this text states so bluntly, is death by suffocation, or asphyxia. Your body's breathing, you're taking in air, but the oxygen can't get where it needs to go. It's a truly tragic example of how one tiny change at the molecular level can have the most devastating life or death consequences. So, if there's one thing you take away from all this, it should be this. Carbon's incredible power, its amazing versatility, it all comes down to its arrangement. Whether its atoms are locked in a 3D fortress or stacked in slippery 2D sheets determines if it's the hardest thing you've ever touched or one of the softest. And whether it's bonded to one oxygen atom or two, well, that determines if it's a killer or a key ingredient in cake. Think about it. From the sparkle of the most precious gem to the fizz in your drink, from simple pencil lead to a silent, deadly gas, this one single element does it all. And the only difference, the only thing that changes, is how its atoms are put together. It just makes you wonder, with an element this fundamental and this versatile, what else can it do? What new forms and functions are we just waiting to discover? What will we build with carbon next?